Welcome to the second video in the Deep Dive series, where we take a common mathematical subject and see just how deep the rabbit hole goes. As a bit of disclosure, I should let you know that from the perspective of a professional mathematician, this isn't very much of a deep dive, it's fairly superficial. But from the perspective of amateurs, this should be a nice overview, bringing together possibly some new topics. In this video, we're going to be discussing trigonometry. Alright, let's start talking about trigonometry. We're going to go through a pretty standard overview of the subject. Namely, we're going to start by talking about sines and cosines in right triangles. Unfortunately, this does limit the angles that you can consider to be between 0 and 90 degrees. And students who have taken pre-calculus may remember that you can take the sine and cosine of any real number. In fact, in calculus, we learn to present sine, cosine, etc. as power series. We're going to run through this pretty standard progression and try to link all of it together. So let's look at these two triangles here. We're going to suppose they have the same angles. Specifically, the angle at the top, A, equals the angle at the top, D, B equals E, and C equals F. If these two triangles have the same angles, they are similar, meaning that ratios are preserved. There's a scalar factor K, so that lengths in one triangle are scalar multiples of the other. And I've specified that side length D is K times side length A, E is K times B, and F is K times C. Now we can observe that we can solve each of these for k. Specifically, k is d over a, it's also equal to b over e, it's also equal to f over c. Now in Euclidean geometry, if you have a triangle, all three angles add up to the same quantity, and it happens to be the same quantity that is the angular measure of a straight line. And for the moment, we're just going to use degrees. We'll call that 180 degrees. So if two triangles have two angles that are the same, in fact, all three must be the same. So more specifically still, if two triangles are right triangles and have one other angle in common, then they must be similar. So suppose you have an acute angle capital A. Any two right triangles that contain angle capital A will be similar to one another. So here are two triangles, both right triangles, and I've put angle capital A in the left corner of both of them. Since angle A plus B1 plus 90 degrees must equal 180, which is also angle A plus 90 degrees plus angle B2, B1 is equal to B2. So here we see that in fact all the angles are shared between the two triangles. Therefore, the lengths in one triangle are scalar multiples of the other. I could pick a specific scalar, I'm going to call it 1 over h1, to make a similar triangle where the hypotenuse will have length exactly 1. And for each non-right angle A, any angle in the first quadrant between 0 and 90 degrees, I could make a reference triangle, something similar, where the hypotenuse is of length exactly 1. So let's go ahead and presume that we've made that triangle. It has angle A on the left, it's a right triangle, and the hypotenuse has been scaled to be of length 1. Now the height y and the width x of this triangle are completely determined. It has to be similar to all other triangles with that angle A and a right angle, and we've scaled it by a specific factor. Therefore, y and x are completely determined, and by definition, we are going to call y, the height, the sine of the angle A, and we're going to call x the width, the cosine of the angle A. We're going to denote these as sine A cos A, notation that many of us are no doubt familiar with. So here we have our reference right triangle. The hypotenuse is of length 1. The left angle is A. By definition, then, the height is sine A and the width is cos A. Well, what if we have a right triangle that has angle A, but it isn't this standard reference one? So here is another triangle, right triangle, angle A, but it's not quite the same. It has an x and it has a y and it has a hypotenuse. But these two triangles are now similar, so ratios are preserved. In other words, there's a scalar multiple, k, so that 1, the length on the right, is k times h, sine A is k times y, and cos A is k times x. We can solve these for that scalar quantity k and see that k is 1 over h. That's kind of interesting, but it's also sine A over y and cos A over x. So here is our non-reference right triangle with angle A, has hypotenuse length h, height y, and width x. And we've solved and found that the sine of angle A divided by y is equal to 1 over h, which is also equal to the cosine of angle A over x. From the first equality, we can set sine A to be equal to y over h by multiplying both sides by y. In other words, y is equal to h times the sine of A. And from the second, we get the cosine of A is x over h, or x is equal to h times the cosine of A. And this is our familiar presentation from high school geometry or pre-calculus, that the sine of A is the side opposite the angle divided by the hypotenuse, and the cosine of angle A is the side adjacent divided by the hypotenuse. So to reiterate, here's what we've established. If we have a right triangle that has angle A, the sine and cosine of A can be defined through certain ratios of sides. The sine of A is y over h, the cos of A is x over h. We might remember, however, that there are other trigonometric functions besides sine and cosine. What are they? Where do they come from? So we've got this pair of similar triangles, and the one on the right has been scaled by k, but we're going to pick that scalar factor in a very particular way. We want the width to be exactly 1. In other words, k times the cosine of A is 1. So the scaling factor we picked, k, is 1 divided by the cosine of A. We define that to be called the secant of A. It's the scalar factor so that the width of the triangle is 1 rather than the hypotenuse. Similarly, we could pick a scaling factor so the height is A. In other words, that scalar factor will be 1 divided by the sine of A, and we define that to be the cosecant of the angle A. And then finally, we can define the tangent and its buddy, the cotangent, through these ratios of sine and cosine. In summary, what have we established for right triangles? All from starting with similar right triangles, the sine of the angle A is the side length across from it y divided by h, and the cosecant is 1 over that. The cosine, in contrast, is the adjacent side length x divided by the hypotenuse h, and the secant is 1 over that. The tangent of A is simply the sine divided by the cosine, which works out to be the opposite side length divided by the adjacent, and the cotangent is 1 over that. But what about circles? In the presentation we've done so far, the angle A had to be part of a right triangle, which restricted it to be positive but still less than 90 degrees. But suppose I just pull out a calculator and say, what's the sine of 0 degrees, or even negative 30 degrees? The calculator will give you a response, telling me, for example, that the sine of 0 degrees is exactly equal to 0, and the sine of negative 30 degrees is exactly equal to negative 1/2. So what's going on here? Well, if we're working in a standard reference triangle, here we have our hypotenuse of length 1, the height is the sine of A, and the width is cosine of A. Place the left corner at the origin, so there we have it. Then, because the hypotenuse of the triangle is 1, that corner lies on a circle of radius 1. Find the coordinates of that corner in the xy plane. Well, since starting from the origin we moved over by a length of cosine A and up by a length of sine A, the coordinates of that point are exactly cosine A comma sine A. And for any angle between 0 and 90 degrees, those will be the coordinates of that point on the circle. So we just extend cosine and sine to be acting on any angle we want by moving around this circle through larger or smaller angles. So in our reference circle that has radius 1, the radius of the circle is taking the place now of the hypotenuse of our right triangle. Here we have the coordinate axes with our circle of radius 1. If you make any angle theta and you measure it as going from the positive x-axis and then going in the counterclockwise direction, you get a ray pointing in a certain direction. You define cosine and sine of the angle theta to be the x and y coordinates of that point. So the point at which this ray intersects the circle is, by definition, cosine theta comma sine theta. Now with sine and cosine defined like that, you can declare the other trig functions to be what we already know they were equal to in the case of triangles. Specifically, secant is 1 over cosine, cosecant is 1 over sine, tangent is sine over cosine, and cotangent is cosine over sine. Now let's try to unify the ideas of right triangle sines and cosines with circular sines and cosines, which does mean we're going to have to be in quadrant 1. So first we have our standard picture with our unit circle. So we have our coordinate axes, a circle of radius 1 centered at the origin, and we're going to put our standard triangle in there that has a hypotenuse of 1, so that can match up with our radius. Second, what we're going to do is draw a similar triangle that has width 1. So it has to go all the way out to the edge of the circle. But now that the width is 1, You can solve for the various other side lengths and find that the height is tangent of theta and the hypotenuse is now of length secant theta. Third, what you could do is draw a complementary triangle here. Okay, so it goes horizontally tangent to the circle at the top and goes all the way out to where that ray would meet that line there. Solving for these, you'll find that the height is 1 because it goes up to the top of the circle, the width is cotangent, and the hypotenuse length is cosecant. So these are all geometric ways of unifying all 6 trigonometric functions, sine, cosine, tangent, cotangent, secant, cosecant, using triangles in the first quadrant through the circle. But now calculus can come into the picture. We've defined cosine and sine of an angle theta as real valued functions for any angle theta. We can do calculus-y kind of things like ask what are the derivatives of these functions, and anyone who's studied any calculus will probably remember that the derivative of sine is cosine and the derivative of cosine is negative sine. We can also ask questions like, are these functions equal to their Taylor series? Once we have derivatives, we can start taking further and further derivatives. We can compute Taylor series, but the astute among us may remember that not every function is actually equal to its Taylor series. What about sine and cosine? Are they? So what you can prove with a little bit of manipulating series is that yes, sine and cosine are equal to their Taylor series for all values of x. It actually does not matter where you center these Taylor series, but they tend to be centered at 0. So for all real values of x, we get the following power series for sine and cosine. These series converge not just for real numbers, however, they converge for complex numbers. So we can now let x be a complex value. So with a complex number z, we simply define the sine and cosine of that complex number through these power series. The circle, the triangle don't make so much sense anymore, but the power series work just fine, so we go with it. These functions are what are known as entire. They are complex differentiable at all complex values, and their range is the entire complex plane, perhaps missing one value. This is a result called Picard's little theorem. In fact, these have range all complex numbers. So many people are surprised that the equation cosine of z equals 42 has a solution. For those who've taken real valued calculus or pre-calculus, you remember cosine can't be larger than 1. So how can the cosine of z be 42? Z is not a real number, it's a complex value. Finding the exact solution is an exercise using the identity that 2 times the cosine of a complex number is e to the iz plus e to the minus iz, but this really isn't about solving exercises. These can be solved, it's not the worst thing in the world to do, we're just not going to spend the time to do it. Okay, what else can we do? The series defined the sine function of any complex argument z. But this can now be extended to any choice of z where multiplication, powers, and division by scalars makes sense. For example, you can take the sine of a matrix, capital A, by using A as the argument. Okay, so using calculus, we've established you can take the sine, cosine of complex values, matrices, or anything where that operation of raising to powers and multiplying by rational numbers and taking series can be defined. But these things aren't angles. Okay, complex numbers do have an angular argument, but that's not what we were taking the sine or cosine of, and matrices aren't even that. So is it still productive to think of sine and cosine of these objects? Yes, it really is. So even beyond their use in geometry, sines, cosines, and now the related exponential functions, all of which can be lumped together for reasons we're not really going to get into, are fundamental in the study of differential equations. Now, differential equations are really not the focus of this video, but it does turn out there is a way to visualize complex valued angles, in other words, what we're plugging into sine and cosine. And here we're working towards a presentation of what's put forth in this paper right here, a geometric view of complex trigonometric functions. So first, let's get rid of degrees. Degrees are bad. It's an arbitrary amount. We just sort of said a circle should be divided into 360 of them. But the circle itself didn't tell us that there were 360. It's a number we chose. A radian, on the other hand, is an angular measure that is intrinsically defined by the circle itself. Now, for those who don't remember, what is a radian? We're going to take a circle of radius r, and we're going to put down 2 radii in it. And these are going to mark off an arc length of length theta r, and that's going to correspond to theta measured in radians. So here's our picture. We have two radii, both coming out of the center, as they are radii. Here they mark off this arc length. Whatever the radius was r, I find a scalar factor theta so that r times theta is that arc length, and then that factor theta is that angle measured in radians. Even more specifically, if I make the circle be of radius 1, then this just simplifies to when you mark off an arc length of a given length, then the angle that does that is that number as a measure of radians. So our circle-based definition of sine and cosine was based on drawing angles in the unit circle, and then we just sort of extended it to go into other quadrants. The circle is defined to be all points a given distance, in our case 1, from the origin. So we get the very familiar formula, x squared plus y squared equals 1. This is just the distance formula. All points x, y, distance 1 from the point 0, 0. And the unit circle is then all of the solutions to this. But rather than considering the formula x squared plus y squared equals 1, which gave us circular trigonometry, for real variables x and y, then you end up making x be the cosine of theta and y be the sine of theta, etc., etc. What if instead we let u and v be complex variables and we require that u squared plus v squared equal 1? Then we can investigate what points in the complex plane are solutions. So we have u squared plus v squared equals 1, and without going over the full derivation, it takes a while and I don't really want to get into it, the solution set is a one complex dimensional subspace of the product of the complex plane with itself. So if we visualize this one complex dimension as two real dimensions, as a space parameterized by an angle theta and omega being real numbers, then u of theta plus omega I is equal to cos theta times the hyperbolic cosine of omega minus I times the sine of theta times the hyperbolic sine of omega. And v, which we got from our solution to u squared plus v squared equals 1, follows a fairly similar but slightly different formula here. So you can verify that this choice of u and v do solve u squared plus v squared equals 1, and they are the only solutions. We're not going to go through all that work. Take my word for it. Okay, so if u squared plus v squared equals 1, all solutions can be parameterized by two numbers, theta and omega, where u, parameterized by theta and omega, is given by this first line, and v is given by the second. If we fix omega to be equal to 0, in other words, u and v are now only parameterized by theta, since the hyperbolic sine of 0 is 0 and the hyperbolic cosine of 0 is 1, we get cos theta and sine theta are familiar x and y kind of stand-ins. So we get our familiar parameterization of cosine and sine as points going around the circle. But what if theta is 0 instead of omega? So here are our complex solutions to u squared plus v squared equals 1, and we're going to fix theta to be 0. Well, since the sine of 0 is 0 and the cosine of 0 is 1, we end up with the following, that u, parameterized only as omega times the imaginary number I, is the hyperbolic cosine, and v is the hyperbolic sine times I, suggesting that hyperbolic cosine and hyperbolic sine are a natural way to interpret sines and cosines of complex angles. So what if we rely on the series definitions and start plugging in complex arguments? We get something very similar. If all you do is plug in I times omega to the power series definition of cosine, you will recover the hyperbolic cosine. And similarly, the sine of I times omega is I times the hyperbolic sine of omega. So we've kind of worked through a lot, starting from u squared plus v squared equals 1, allowing them to be complex numbers. All possible solutions are parameterized by two parameters. We called them theta and omega. Setting omega to be 0, we recover our standard cosine and sine of a real valued angle theta. And letting theta be 0, so we have a purely imaginary argument omega times I, we ended up with the hyperbolic cosine and I times the hyperbolic sine. And since we imagine cosine comma sine when we're working with real valued angles to be points in the plane, what if instead we looked at the hyperbolic cosine plus I times the hyperbolic sine? This also gives us a single point in the complex plane. So that will plot as hyperbolic cosine comma hyperbolic sine. So we're going to be plotting hyperbolic cosine, comma hyperbolic sine to get a point in the complex plane. These exactly solve x squared minus y squared equals 1, a standard hyperbola. Hence the term, by the way, hyperbolic cosine and sine. So the path from 1, 0 to cosh 0 sinh 0 to the point cosh omega sinh omega goes up in this direction. And the length of that path will be exactly omega. So omega is parameterizing a length on a hyperbola. So think back to how radians were defined. An angle of theta measured in radians in the unit circle exactly makes an arc length of theta. But now we've actually seen that a purely imaginary angle of omega times I creates this arc length of exactly omega in the standard hyperbola. So instead of radian measure giving us arc length in a circle, we have this imaginary measure of angle giving us a length in the hyperbola. But really, you shouldn't just take my word for it. Okay, I gave you the source earlier that I'm deriving this hyperbolic presentation from. Go to that original source. The classic derivation of hyperbolic cosine and sine just from the hyperbolas is hundreds of years old. You can find it in just about any textbook. This paper that I'm linking to really does a better job, however, of linking it to the equation u squared plus v squared equals 1, which isn't always fully worked out. So here's the link again. Richard Hammack's paper, A Geometric View of Complex Trigonometric Functions.